So thank you for having me today. So I guess when I wrote my abstract, I put a lot of things there. But basically, the idea will be to talk on to divide the talk in two different parts. So maybe what I will do is I will present the first part, and then after we can have some questions and opportunities for you. For you guys to ask some questions and for me to answer them, and then after we'll move to the second part. So for this first part, I'm going to talk about global scale paleo landscape evolution and basically how we try to design and develop new models to answer questions related to the evolution of the Earth over several millions of years at global scale. So specifically, what I will do during this talk, I'm going to this part of the talk, I'm going to really look at paleo-elevation. So paleo-elevations, they are, as you can see here on the image, they are basically a snapshot or time slice of the evolution of the Earth through millions of years. So here you've got a time step, I think for this of 5 million years. So every 5 million years, you've got an image, and you've got about 100 million years of Earth evolution here. So this paleo-elevation, they are actually you can say that they are not really quantitatively assessed. It's more like a kind of a qualitative approach where people will have some information, I don't know, from fossil records or from exhumation rates about potential environments and potential elevation of a specific place, and then after they will draw basically what they think the landscape or the elevation was looking like. So even if it's quite qualitative, this kind of approach, or this kind of paleo maps and paleo elevations, they have been used intensively in many different fields. For example, every model that you look at, which are paleo-climate models, basically they will rely on a paleo-elevation. If, for example, we look at paleo-biodiversity or the evolution of life, most of the evolution is going to be driven by these landscapes that you see here, or if it's not the landscape, it will be the elevation gradient. So the slope between, that is changing over time. And as I was mentioning before, even if they are crucial to our understanding of the history of the evolution of the Earth in terms of biodiversity and also climate, they are still not really an easy way or a nice way of quantitatively assessing them. So the idea of this talk is to present a new model that I've developed, which basically try to overcome some of these problems. And so if we think about the geomorphological expression, or if you want what you see on the left here, which is like a representation of the elevation of the Earth at a given time interval. Basically, it's a combination of the interaction between different things. So the surface, you can imagine the surface as basically the surface of your skin. So it interacts with the air, but also all the things which are happening inside your body. And this will be the same for the Earth. So you will have basically the interaction with paleo-climate. And also the interaction with tectonic forces that are going to, uplift or subside part of the crust and change the paleo elevation accordingly. And of course, if they are like proper representation of the surface of the Earth, they should also include erosion and deposition, which is the central part here. The middle thing in the graph, which is basically what we try to do. So trying to evaluate how sediments are going to be moving across the landscape and change basically the elevation as they evolve. Of course, when this kind of paleo elevation are created, there is usually what is happening is you create a paleo-elevation, then someone is going to run a paleo-climate on top of it. And then after you might have some people looking at tectonic force and mental evolution, and basically use this as input to their model. So basically the arrows that we see here that are going from the right to the left, in reality, what is happening, at least in geoscience, is at this scale, basically it's going from the left to the right, okay? So the idea is how we can try to see how wrong basically these paleo-elevation are and what we can do to improve them. So to do that, basically I've design a tool. So I've designed several tools over the years, but basically this is quite a simple tool. It's going to evaluate the evolution of the elevation over time and you can impose different things. So you can impose the uplift, so a tectonic forcing. And then after you will have some climate, some rainfalls that are going to vary spatially and temporally. And this climate is going to, basically you look at the precipitation. This precipitation is like small drops that are going to form rivers. And as these rivers are bigger and bigger, you start to erode some sediments. And then after, depending of the landscape, depending of the slope, or depending of basically if you are in a depression, you might end up depositing some of these sediments along the way. Another process that we try to simulate in this model, apart from like the river and the fluvial processes, is also the hill slope processes, which is like, a diffusion equation here, where basically you will have the slope that is going to drive some gravity flow and move the sediments down the slope. Okay, so that's the two main basically components of the tool. And the idea of this tool is basically you've got the equations that I've just described, like really briefly in the previous slide, so which are part of the gospel engine. And then after to run the models, basically you need a set of inputs and you will get some outputs. So in this specific case, what we are going to do is we are going to test the paleo-elevation reconstruction. So we are going to use as input some paleo-elevation models. Of course, we will need some climate models, so mostly precipitation, to basically force the model with some rainfall. And then after you can impose, if you want, some tectonic forcings that are going to move the surface up and down depending of the tectonic fields that you impose. At the output of this engine, you will have a set of different results that you can look at. So you can look at the evolution of the landscape, so meaning how basically different catchment are going to change, where the drainage divide is going to move, how in size your landscape is going to be, but also you've got output associated to river and sediment fluxes, and also we are able to basically reconstruct the basin evolution. So when you've got like depression or when you are entering the marine environment, you will start to deposit some of these sediments and you will deposit them in a kind of a stratigraphic layering, and you can evaluate how this stratigraphic layering is similar or dissimilar to observation. So when it comes to the outputs that you get, basically there is a set of different data that you can compare your model with. So first there is some information about paleogeography, so that will be like, for example, fossil records. You've got also potentially some seismic for different regions, and so you will be able to compare the stratigraphic record from observation, from seismic, for example, with the stratigraphies that you get out of your model. And if you are in mountain ranges, potentially you will have some idea about the exhumation of some old rocks based on dating, and you will be able to compare that with the exhumation rates from your models. So there is this kind of things that you can use to evaluate how your model is performing and how well is able to simulate part of the observable. I'm going to yeah, so I can just talk briefly about that, but basically the code is open source. It's available via GitHub, and one of the main difference between this landscape evolution model and the ones that are on the market at the moment, I guess, is the fact that the model is based on we have parallelized the code, so we can run it on a supercomputer, and that's why we are able to run it on a global scale, on global scale and over millions of years. And to do that, basically, most of the model I'm going to show today, they have been run on Artemis, so the Sydney Uni supercomputer over several hundreds of CPUs. So what we do to evaluate basically the paleo-elevation, we start, let's say, at a paleo-elevation at 55 MA. We can impose some tectonic, some climate. We can, on top of that, use our global scale landscape evolution model, run some surface processes, and evaluate that against another time step of paleo-elevation that is that is given as the input. Okay, so what we see on the left and on the right here, these two globes, basically they are the input. Okay, they are coming from a paleo-elevation reconstruction, and what we can do is, once we have applied this tectonic, climate, and surface processes, is compare what we get with what we should have if the paleo-elevation were correct. Okay, so what it means that we need to do some adjustment potentially to basically see how different our model is from the observation. Okay, and so we do that over like several millions of years, 100 million years, or we can do that over 500 million years. And so what we do is we assimilate over time this paleo-elevation, and to do that we need to basically we use a kind of a stepwise matching approach, which basically is going to ensure that over time we are adding the long wavelength representation of the paleo-elevation that is conserved as we move forward. And so to do that, we are using a filtering technique which is based on spectral analysis, but I'm not going to enter too much into detail here. But basically the idea is that we want to ensure that we conserve the long wavelength. So where we should have some mountain range, we want to have some mountain range as we move forward, but what we want is we want to keep some of the information coming from the surface process model. So the surface process model, for example, they are going to provide us with a bit more granularity in terms of elevation. We will have some places where we'll have some incised valleys that are going to appear, which are not visible in a paleo-elevation model, because the paleo-elevation reconstruction is pretty coarse. So we want to make sure that we keep this information from the surface process model as we move forward in time in the modeling domain. So here is an example of such a model over like 100 million years. So what you can see is that there is some valleys that are formed, or some channels that you can see here that are going to, sometimes they are going to be continuous over time. So they are going to develop further and further as we move in time. Other time, you see that there is some depression or some change in the landscapes that will drive basically some change in the river pathways and in the deposition and erosion. Okay. So once you have a model like that, basically there is a lot of things that you can extract from it to try to understand first how the paleo-elevation is actually what the results that you get, how different they are from observation once you have included now the surface processes model, and also to see if there is any things that you can potentially change in this paleo-elevation to make it fit better with observation. So first things that you can do is you can extract from this model. As I was saying, you've got on the left here, you've got an idea of the river flux and sediment flux, and also the distribution of the main catchment. What you've got in the middle here is a representation of places where you've got erosion and deposition. So erosion being in blue and deposition in red. And also what you have is you've got a global representation of the stratigraphy. So the stratigraphy is basically, you can see here, it's a slice through the globe here around the equator, where you can see the record of sediments which have been basically transported by the rivers or the hill slope processes from the sources, which, you know, in this case, we are close to this is the Amazon fan. So basically it will come from the Andes, I guess, and being transported and deposited in the Amazon fan. Okay. So we've got this record at different stratigraphic layers that you can basically compare after with some data, and I will show that a bit later. So that's the first kind of output that you've got. Another thing that you can do is you can start to look at basically how the drainage basin are distributed over time, how basically the water discharge is changing, and where are the places where you will have, you know, depending of the times that you are looking at, you know, where you will have a large influx on a specific region, and other place where it will be pretty low in terms of sediment or water discharge. Okay, so here we are looking at water fluxes, but you can do the same with sediment flux. Okay, what you can do also is start to make some comparison between what you get out of the model in terms of distribution, for example, of basin drainage area versus water discharge, and look at, you know, how it compares with the distribution of present day catchment and discharge. So here you've got in black, you've got the present day value, and in the circle, the white circles, they represent the simulated data. So overall, and this is for basically at the end of the simulation after 100 million years of simulation. So what you see is that most of our catchments, they have pretty much the same size and the same kind of water discharge as the present day values. So of course you can do that over, you know, the entire duration of the model. So in this case we run the model for 100 million years, and you can compare how much sediments it delivered to the ocean over time, and you can compare that by dividing also in, you know, are you in a specific latitudinal range, so subtropics, temperate, and polar. And the idea is that this is quite important, because you can use this kind of sediment flux to get a sense of what are the causes that drive these changes in sediment delivered to the ocean, but also because the sediment delivered to the ocean has a huge impact on, for example, strontium isotopic content in the ocean water, which is something that we can that basically we have a record for you know, several millions of years. So you can compare what you get from the model with this kind of record, but also, like for example, if you are looking at biodiversity, there is a strong correlation between sediment influx to the ocean and the apparition or the flourishing of life in the ocean, because most of the rivers are also delivering nutrients to the ocean, and so there is a strong correlation between the two. So having some information about how much sediment is actually delivered to the ocean at this kind of global scale is important to answer this type of problems. So the model I've shown here is a model that is run over 100 million years at a resolution of about 10 kilometers, which allow us to first look at what is happening at global scale, but also to look at what is happening at catchment or more at regional scale. So to give you an idea of this, here is an example of the sediment flux, which is distributed by the, which is going out of the Orange River in South Africa. And what you've got, so basically what we do is, what you see is the dots here, they represent the reconstruction of the outlet over time as the plates are moving. And for this outlet, okay, of the Orange River, what we do is we record the sediment flux, which is going out of the outlet. And the result is the green line, or the teal line, I guess, here, which shows basically in the background what the model is predicting. And what you've got, the teal actually is the measured value, which are extracted from stratigraphic record. So looking at the accumulation of sediment in the ocean and basically dating these sediments. And what you've got in orange is what the model is predicting. So overall, there is it's not a perfect match, but basically what we've got is we've got really a good representation, I guess, of the first order evolution of the Orange River, which basically give us some confidence about how the paleo-elevation is actually mimicking, the evolution of the region during that time interval. So it gives us some confidence about the quality of the paleo-elevation, of this specific paleo-elevation for this region. So another example of what you can do, again, at a more like a catchment scale, or let's say regional scale, is we look at different places, and here is in South America, where we did a different cross section, and basically you can look at first what is the shape of the deposits. Do we have like a long thin sediment which are deposited, or is it like more like a kind of big large or rapid deposition which is going on, and you can compare that with some data. So here, for example, for the section 2, we are looking at offshore of South America here, the Pelotas Basin, where you've got the predicted stratigraphy from the model, and for example 2D seismic cross section, which shows if the how the model is performing for these specific places. An example which is interesting is the section 3 here, where basically there is a complete, not a complete, but there is quite a significant difference between the stratigraphic that is recorded in the model and what the seismic is actually telling us. What it shows is actually that there is a big a kind of a mountain range or eye in South America, which actually start to form much earlier than what is provided in the paleo-elevation. And so what we see is that actually the model is not able to reproduce the stratigraphy because there is some problem with the paleo-elevation for these specific places. So this gives us some idea about where potentially there is some things which are wrong, and how we can potentially change the paleo-elevation to get better prediction. Another way of doing that is basically to look at river networks and look at the evolution of the rivers. You can see here in the rivers there is sometimes a change in slope, which is called a knick zone, and these knick zones, they are propagating due to change which are can be a lithological change, but also are often related to tectonic change. So as you start to uplift one portion of your river, you've got this steep slope that is basically starting to go upstream towards the top of the catchment. And so you can basically have an idea of how fast this migration is happening, and it gives you some idea about how strong the tectonic signal was. So this is the kind of information that you can also extract and try to compare with basically the longitudinal profile from different rivers. Just to conclude on this section of the talk, basically what we've got is we've got a model that is able to simulate basin accumulation through time, and that you can calibrate using different things such as exhumation rate or paleogeography maps. And this model can be used at global scale, but also at local scale. And I think I will let it there for this first part of the presentation. Okay, so I'm going to keep talking about landscape dynamics, but this time I'm going to move from global to more local kind of approach using the same tool, but this time trying to see what we can learn from landscape dynamics in terms of how it might have drives the evolution or the migration of species around Southeast Asia. So I could not start without showing this awesome diagram from von Humboldt in 1841, which basically shows how not just elevation, but how basically elevation gradient and elevation change are actually having a huge impact in terms of what species you are going to find in a particular place in the landscape. So there has been a lot of questions, and I mean it's still a big part of what people are trying to solve. But basically, what is driving the diversification and the migration of species across the landscape? And of course, there is different factors that are going to impact on that. First one, there is biological factor and abiotic factor. So in this second part of the talk, and really this is a big disclaimer, I'm not going to solve everything. I'm just going to basically look at the impact of landscape and of landscape changes. Okay. So to do that, and of course, most of these abiotic and biotic factors, they are going to they are acting at different spatial and temporal scale, and they will all have a huge force. They will have a huge impact on the evolution of species. Oops. So why we decided to look at physiography evolution or landscape evolution is because in most cases, if we look at how people are looking at landscape in biodiversity approach, usually they will take landscape as a steady state or as a kind of a simple change in gradients, and basically they often overlook this component in their model. So, for example, here you've got a representation of the Alps or the Rockies or the Himalayas in terms of elevation gradient and distribution. That's basically histograms, or hypsometric curves of the distribution of the elevation, the area of the elevation with elevation. So usually this is going to be quite simplistic, and we all know that in nature the landscape is really transient, and that there will be a lot of geomorphic responses which are going to happen really fast. For example, if you've got a flooding event, or if you look, for example, at river captures, it can happen over days, and sometimes it can happen over millions of years. So there is a lot of changes that are happening, and basically in the way people have been looking at species migrations, they haven't really put a lot of effort in trying to simulate those changes. So again, I'm not going to define that, but basically we use the same kind of model. And what we can do is we can test different elevation, different climate, or different tectonic scenarios, and evaluate, first how the landscape evolution component is working by comparing it with observation. So what kind of information we've got for Southeast Asia? First, in terms of elevation and tectonics, we've got several morphological indicators, so such as where are the position of the modern and fossil reefs, where are the place where we've got some information about the stratigraphy, and basically we can from that we can also already have some ideas about the tectonic forcing in the region over the last million years, we'll say. So we've got, for example, this part which is between Thailand, Borneo, Sumatra, and Java, which is called Sandaland, is basically subsiding. So that's the. Can I use my mouse here? No. So that's the Sanda shelf here, where you can see the big minus here. It's basically this place is subsiding since over the Quaternary. Okay. We've got some information that we can back up with, some seismic distribution of the basically evolution of the trench, which is just following the Java continental shelf and continental slope here. And we can use that basically to get a sense of the distribution of the tectonic forcing, so uplift and subsidence in the region. What was found is actually up to, let's say, 10 years ago, people were thinking that, even less than that, but basically people were thinking that this Sanda land region was intermittently flooded due to sea level change. Okay, what actually these new findings about the tectonic forcing in the region shows is that actually before, let's say, 500,000 years ago, most of the region was actually terrestrial. Okay, and so you can use different conditions of tectonic or subsidence rate. In any cases, you end up with basically a place which is continental over the last before, permanently continental before the last 500,000 years. So for the climate, what we use is a paleo-climate model, and the data is available from the paleo-climate dataset. And so we take this information and we run the model over time. What we are looking at here is a specific snapshot. So what you've got on the left is the paleo-elevation, the elevation, if you want. And on top of that, overprinted, you've got the main drainage, the main rivers. And what you've got on the right is the main catchment. So each of these big color here, they represent like a large catchment with a singular plate. So we can do that over different time intervals. Basically, the way we did that, we've got an output every, I think, 1,000 years. And so we can evaluate first the landscape dynamics, and we can also look at river fluxes and sediment flux. Okay. So once you have that, you can compare that with data that exist for the region. And so you can, for example, compare that with seismic and well data to evaluate if your model is reproducing the same amount of sediment accumulation and erosion that the data is showing. And once you are confident with the data, the output of your model, you can move to the second step of the talk. So once you have something, so of course here we haven't just run one simulation, we are testing different things. So we are running a model with no subsidence and a specific sea level curve, one with uniform rainfall and a specific sea level curve, one with different condition of tectonic, so uplift and subsidence, different type of sea level, different type of precipitation, and we look at basically different response of the landscape in terms of the different catchment, and when this catchment, for example, are combined and form a large big catchment, or when, for example, you've got a river that start to be captured from one catchment to another, and look at, if there is places where different catchments are becoming disconnected. And you can, as a first order, you can basically compare that with, different the evolution of different species, and or basically it correlates with some of these large-scale dynamic landscape changes that you see. What we can do as well is use these results from the landscape evolution model to start to design some cost function or cost maps that are going to be used after to evaluate how hard it is to move through this landscape. So you can use the erosion deposition, you can use the slope, we can look at the distance to rivers. We can assume that rivers are going to be a barrier or a corridor for migration, depending on the species that we are looking at. And from that, basically, we are able to extract, to define a cost map or a resistance map for species to evolve and to move across the landscape. Okay. So, of course, most of the people have been using this kind of cost maps. This is not new, but most of the time they are using a kind of a least cost path to calculate, what will be the easiest route to move from point A to point B. Of course, I mean, one of the big limitations of this is basically you are considering that you've got a specific species which has, an iPhone with a Google map, and basically it knows all the landscape. And not only he knows, the most effective way to move from one point to the other, but also is willing to take this route. Okay. So, well, our idea was, okay, so instead of doing that, is there, a better approach that we can use to evaluate species migration across the landscape? So we used a first model, which is based on circuit theory, which is called a circuitscape. It's open source, which basically is going to help us to capture the dynamic at play in travel decision by using this cost map. So we are basically doing a cost map for every time steps, and every time we run this circuitscape model on top of that, and what it's going to highlight is places which are here in yellow, which are like places which are the most likely to be used by different species to move from one point to another. But as you can see, it's not just a single line. Basically, it gives us a corridor of potential migration. Okay. Another example, and this is the last example, it's good, I've got for 15 minutes, is like, can we use also this map to potentially look at the migration of Homo erectus across Southeast Asia and across Sundaland. So there is different fossils that have been recorded that have been found of Homo erectus in Java, but there is still this is still controversial, the age of this fossil. So depending on the dating techniques that has been used, sometimes the range go from 1 million years ago to 1.8 million years. Okay, so this is quite a big range. Here, I'm not going to discuss, what are the problems with different techniques of dating, but basically what we use here is one of the latest datings that has been done, and it gives a broad time of 1.8 million years. Okay, so we use this. I'm not going to go. Okay, about 1.78, so 1.8 million years. So what we can do is we can use the map, and first you can do the least cost path, as I was mentioning before, and from going from different routes in the north here, the green dots, to basically the pink one, the Java position where the fossil is. If you use the least cost path, you end up with a distance to walk from the north to the south of about like 6,000 kilometers. Okay. What we decided to do is, instead of doing a kind of a least cost path or a circuitscape model, is basically to try something else and use more like a kind of a mechanistic movement to move it's not an individual, but basically the group of Homo erectus from the top to the bottom. And so we used Levy-Walker, where we've got random walk in some cases, or correlated random walk, and the correlated random walk is basically going to be used to define a perceptual range that we set here at 5 kilometers. And what is going to happen is like the movement of the walker from one step to another is going to depend on what the walker is able to see in a 5 kilometer radius around its current location. Okay, and the walker is going to take the path that is the one with just with the lowest resistance. Okay. And so what we did is we used that for the different routes, and we did that, and every time we recorded the cumulative distance that was walked. In some cases, it didn't reach, of course, the position, the Java position, but basically we did that for I think for each potential green position at the north, we run like 1,000 simulation. And so from that, after we got a distribution of the most likely path that Homo erectus will take. And what we end up with is basically, so what you've got on the left here is the least cost path of about like 6,000 kilometers. What we end up with, if you use the random walk and the Levy-Walker, is something which is more of the in the range of 320,000 kilometers. Okay, so much longer, much longer in distance. Yeah, and oops. And what you can do, if we've got an idea of the migration speed of Homo erectus, basically we can get a range of the time that it took for him to move from the northern point to the southern part. Okay, and so there is different range that exists. There is a fast migration, which is about like 10 kilometers per year, and a slow migration, which is about 1 kilometer per year. It sounds like it's not a lot, but you have to think about it as the peopling of a specific region, where, of course, people will go around, but they will have a camp somewhere, and they will potentially move over, with time in different places. So what these kind of things provide us is, first, there is a lot of change in terms of landscape dynamics in Southeast Asia. And this physiographic change, either via drainage organization or river captures, they will have a huge impact on species migration. Okay, we can derive different resistance maps that can be used to look at species migration, but also we can also use different type of tools to go beyond basically the least cost path model. And it provides us with some idea about, how Homo erectus has moved, and what would have been the most likelihood places to find some remains of Homo erectus in Southeast Asia. So that's it. 10 minutes. That's good.